What we're going to do next is reorganize these steps of the simplex method in a way that lets us perform these manipulations much more quickly than you saw in the pre-simplex method and really streamlines the process. And so to illustrate that, I'm going to revisit the example that we worked through before and the various steps, and I'm going to show how you would perform those same steps in sort of an abbreviated fashion that uses what's called a simplex tableau. And so to start, what we'll do is we'll revisit with the same example that we had before. This was an intermediate step in the simplex method where we had the basic set that was x1, x5, x6. This was the setup that we had there. And the first thing I'm going to do is I'm just going to take all these non-basic variables and I'm just going to move them back to the left-hand side where they were before. So what I'm going to do now is get this system down here. And what I did is I made little notes to myself. I said, by the way, this is the row for x1, this is the row for x5, this is the row for x6, just as I had up there. I'm making those little notes to myself so I can remember what the basic set is. And then other than that, all I've done is I've just moved these non-basic variables back over here like this, okay? So this is the exact same system. I've just brought those non-basics over to the other side. That means I have constants over here. And as well, I have this constant that appeared in my objective function, which is now up here in the upper right. I've decided to write it there. Now remember, this constant only appeared because of the way that my objective function changes with respect to my basic set and my non-basic variables. So that's why you have that constant there. Let's just work through those steps, or just look at those iterations of that simplex method now within this kind of notation, just so we can get comfortable with that. So we started with x1, x5, x6, as you see here. And then we moved along, and our next set was x1, x3, x6. And so we had this system here, and so I've just made notes of 1, 3, and 6 like that, and I just copied this system over. And I really want to say there's nothing really interesting that I'm doing here. Literally all I am doing is moving these non-basics over to that side. That's all that is going on. Okay, and I guess I'm making little notes to myself about what the basic variables are by putting a variable to the left of those equations. But that's it. Okay, that's really the only thing that's going on. And so what we're going to ask ourselves, this was the last step here, I think, or one more. What we're going to ask ourselves is, how do I get from one step to the next? If I just look at these tableaus, if I look at the lower half of the screen for all of these, how can I get from, well, this is the final step there, but how can I arrive at that final step from this step over here, right? Is there a way I could do this without going through that whole song and dance of solving for these variables and then writing down all these various things, right? Is there a way I can go from the one table into the next? So let's look at one example here. Let's say I've got the basic set of 1, 2, 6 and 1, 2, 4. Okay, and let's look at this and let's say, well, there's two things that change. The objective function changes, all right? You go from this thing, 62 minus 9, and so on and so forth, down to this thing over here. The objective function changes, and the constraints also change too, right? This right-hand side vector changes, and all this stuff changes. Of course it does. Let's look at the constraints first, okay? How do I modify these constraints? How do I take the constraint system and go from one step to the next? Okay, so how do I go from, let's see if I can do a nice little rectangle around that. How can I go from this system over to this one? Alrighty, and let's look at what really characterizes these systems here. The thing I want to observe visually before I explain the actual process is to say that this system here is expressed in terms of x1, x2, and x6, and that's reflected in the fact that x1 only appears here, x2 only appears here, and x6 only appears here. And I want to do something with this system to transform it into one that has an x1 over here, an x2 over here, and an x4 that only appears over here. So you want to reflect this idea that the 6 is going away, and the 6 no longer has this special status, and that it's now x4 that's going to have this special status. Okay, so how does this happen? What are the two things that we want to have happen? The third row had an x6 in it, and it was the only row that had an x6 in it. And we want to change that to have going to then having an x4 in it and being the only place that has an x4 in it, right? So once again, let me erase this just to emphasize that. Okay, the thing I want to emphasize again is that you only have, in that first step, x6 only appears in this third row. Okay, it only appears once in that third row, and it's because this third row came from, solving for x6 as we had before, right? That's where that came from, and then we want to change that so that instead of being x6 that is special, it's now x4 that is the only thing that appears there. All right, so how do you do that? Well, what do we want to have happen? If you think back to linear algebra, what is it that we want to do? I said we want to have x4 appear in this location here and have nothing but zeros up there. What does that mean we want to do up here in this example? It means we want to take this x4 and we want to do row elimination, Gaussian row elimination, to zero this thing out and to zero this entry out. What's going to happen when we do that? When we zero these entries out, it's probably going to fill up non-zero entries here and here for x6. And that's fine, and that's reflected in what we have over here. So the bottom line is, what are we going to do to get from one step to the next? We're just going to perform Gaussian row elimination. And in case you don't remember how that goes, we'll work through that many, many times here, and I'll just work through that one example there. So let's copy down this system here. I've got x1. Then there's an x2 in that second row there, so we'll put that there, an x1 and x2, and then a minus 3x3, and I'll just write out that first row here. I'm doing these variables in a really strange order just to keep my columns aligned. Plus, and that's not a 4, that's just an x4, minus 1/2 x5, and then there's no entry x6 there, and that's equal to 50. And then the next row had an x2 plus 7x3 minus x4 plus x5 is equal to 50. And then finally, I've got minus 14x3 plus x4 minus 2x5 plus x6 is equal to 30. Okay, and so what do we want to have happen here? So these two entries here, when I do the next video, you're actually going to be able to see my hands, and it's going to make this a lot easier. But for now, I'll say, okay, these two entries here, this minus x4 and this plus x4 in the first and second rows, we want to zero those out. We want those to be 0. So what does that mean it should do? I'll put Roman numerals here for this will be row 1, row 2, and row 3. And what do I want to do? I want this x4 here to be a 0, which means I should take row 3 and I should add it to row 2. Okay, so take every entry in row 2 and then add the corresponding entry in row 3. Again, if you could see my hands moving, you'd be able to see me gesturing at which entries are going to vanish, and you'll see that in the next video. So if this isn't crystal clear right now, you'll see better examples of it in the future. But let's work through this right now. Okay, let's go through one entry at a time. Again, I want to zero out the x4 in the second row, and so I'm going to take row 3 and I'm going to add it to the second row. So what happens here? So x1 does not change, x2 does not change. In this the x3 coefficients here, I'd be taking minus 14 and adding it to 7, which would give me a negative 7. And I'd be taking an x4 and adding it to a negative x4, which zeroes it out as I want it to be. Then I'm taking a minus 2 and adding it to an x5, which means this becomes a minus x5. And then I take an x6 and add it to nothing, which becomes a plus x6. And then I take a 30 and add it to 50, which gives me 80. Yeah, a pen is a terrible medium for doing Gaussian elimination because I can't erase anything. So sorry for how ugly this looks. I'll zero out this x4 in the top row too, and the way I'll do that, since I have a plus sign next to it, is I will subtract the third row from that first row there. So x1 doesn't change, x2 doesn't change, minus 3 minus negative 14 x3 is minus 3 plus 14, which is 11. So this is now plus 11 x3. Okay, and then the x4 minus x4 zeroes out, and then the minus 1/2 x5 minus negative 2 x5 is now a positive 3/2 x5, like that, and then the 0 here minus an x6 is a minus x6, and I have 50 minus 30 there, which is 20. Okay, and so lo and behold, what have I done? Now I've got an x4 here, and then I've got some x6s over there. But the key thing is, as I wanted, I now have x4 appearing only in that second row. So rather than look at my messy handwriting, I'll show you the pretty version of it, which is right here. Okay, you can see that just by adding, doing those row manipulations, I ended up with exactly the system that I wanted. Right? If we go back to when I posed the question, I said, how do I get from this one tableau to the next? If you erase all this stuff out, you can see that just by doing those two simple row operations, I actually got exactly what I wanted. And that's the key to all of this. It's that actually to get from one step to the next, you just do one iteration of Gaussian row elimination, and you're all set. Okay, so we now know here's how you change those constraints. We now know how you go from one constraint system to the next. You just do Gaussian row elimination. And in fact, the same thing is also true for the objective function. Okay, so previously we had this objective function here, minus 64x3, and so on and so forth. Or sorry, this is what we ended up with. We started with this one up here. And we'll ask, how do I get from this objective function down to that one? And in fact, you do the same thing. You perform Gaussian row elimination again. And let's work out where that comes from. Okay, so we start with this objective function here in terms of some non-basic variables, and we want to express it in terms of the new non-basic variables, which are the other terms. So you want to go from 3, 4, 5 to 3, 5, 6. And so what does that mean? We want to get rid of that x4 term, and we want to replace it with an x6 term, just as we had happening before. And so what does the third row say? The third row, which is the row that I had expressing x6, it says this here. Okay, if I go back to the third row of that upper system there, you'll see exactly that. So the third row says that, or rather, yeah, minus 14 and a 1 and a 2. Yeah, this one, this row right there. 1, 2, and an x6 has there. Good. It's the third row says this, and I can rearrange that so I have a 0 on this side. Okay, just subtract the 30 off there. And now I have this expression here, which is equal to 0. Okay, it has to be equal to 0 by that constraint, which means it's equal to 0, so I can add it to anything I like, right? If something that's equal to 0, well, I can add it to anything, and I won't change it because it's still 0. So let's take this expression, which is equal to 0. Let's multiply it by 9, and let's add it to the objective. Now, why did it occur to me that I should multiply it by 9? The reason I'm going to multiply it by 9 is because I have a coefficient here of x4, and I have a coefficient of 9 of the x4, which is how I'm going to try and zero it out. Okay, so what do I mean by this? I mean, I'll take the objective function, this thing here, and I'll just add 9 times this other expression, which has to be 0 according to that third constraint, and I end up with this thing, which is just what I wanted. All I'm really doing here, again, is just Gaussian row elimination. This light here is just a proof, so to speak, that Gaussian row elimination on the objective function also makes sense. And so that's a bad explanation of that, but what I really want to communicate here is this full final simplex process, which is what you see here. So when you do the full simplex method, when you're doing the simplex method as your problem set dictates, you use what's called a simplex tableau, okay? And that's this thing down here. This records all of the information that encapsulates this problem. Okay, so here's, you've now seen me do this sort of row expression for the various iterations for this thing. Okay, this is some intermediate step of the linear program with the basic set of 1, 5, and 6. And we'll compress all of that information into this table down here, because we don't need to write out x1, x2, x3, x4. We don't need to write the variables. We can just write the coefficients. That's why linear algebra exists. And so what you do when you write a simplex tableau is the following. You have a table, and your first row here, you write this little separator here, or a line, because the first row of this table is just the objective function coefficients. Okay, so that's 1, minus 31 on 2, minus 93 on 2, 13 on 2, and a 0 and a 0. And notice here I've got a plus 1195, right? That just happened to be what the constant term was for my objective function there when I did the manipulation. But you'll notice down here I write negative 1195. So this is an annoying little thing you have to remember about simplex tableaus, and you'll be seeing a lot of this. Whatever the constant is in your objective function, a bunch of variables plus some term, whatever that term is, you multiply it by -1 and put it in the upper right-hand corner like that, and you'll see how that ends up being useful later. But for now, you'll just have to trust me. Okay, and then the rest is just the coefficients of this stuff, the coefficients of these expressions, and you put them in this table down here. So it's really just like writing the whole system in a big matrix, and really the simplex method is nothing more than sort of a Gaussian row elimination with a little bit of extra bookkeeping to take care of. And then I always just write a letter B there to remind myself that the leftmost column is where I talk about the basic variables. And in this case here, it's x1, x5, and x6. So I like that. That left-hand row should just mention what the basic variables are. Okay, and now let's look at an iteration of the simplex method using the tableau. So let's go from this tableau to a new one. Alrighty, so this is, let's say we have this tableau, and what do we look for? What are those steps from the simplex method correspond to now in this new setting here? You're going to find that visually this process becomes a lot simpler. So let's say this is in the process of solving a linear program. I have this tableau, which you now know how to compute. And what do at this point? You look for a negative objective coefficient, right? And you'd say, yeah, you've got 2, you've got a minus 31 on 2 and a minus 93 on 2. And so let's say that x3 is going to enter the basic set. So we'll say, okay, this is the column that's entering. x3 is going to enter, and it's going to replace x1, x5, or x6. And how do we determine which one leaves? It's by this minimum ratio test, right? You ask which of these variables can I is gonna zero out the first. But thanks to this tableau, that minimum ratio test is now really, really easy. All you have to do is take the right-hand column here. You take these entries and you divide them by the strictly positive entries in this incoming column. And there's 2 of them, right? So you'd look at 75 on 1/2, and you'd look at 50 on 7. And you would not look at 130 on 0, because there's a 0 here, which means that this row does not care about x6, and so you're free to make x6 as, you're free to vary x3 as much as you like without affecting x6. So we look at 75 on 1/2, and you'd look at 50 on 7, and you'd find, therefore, that x5 is going to leave because 50 on 7 is the smallest. So then you'd make a little note, and let me make sure I want to erase that arrow there for x6. And then what I would do is I would draw a little arrow like that, and I would say, okay, now I know what this step looks like. I'll erase all this stuff too. Now I know what needs to happen. I know that x3 is going to enter my basic set, and x5 is going to leave. And then I have to perform some Gaussian row elimination to accomplish what? What needs to happen here is x3 is entering and x5 is leaving. So that means that I want a 1 over here, and I want zeros in all these other places. and then and that's all that needs to happen. So I just have to zero out these entries where I put the x's, and I need a 1 right over here, and then I'll have successfully moved x3 into my basis. So let's look at the linear algebra here. So I want x3 to enter, and x5 has to leave. So what needs to happen? So row 0 should have a 0 in the x3 column. So I want a 0 over here, just like I put the x in there before. And there should be a 0 over here, and there should be a 1 over here, and there needs to be a 0 down here where there already happens to be by coincidence, and we're happy about that. Okay, so how do we make this happen? Once again, I'm going to work this through with my hands in a few minutes, and it'll be easier for you to follow. So hopefully these slides are helpful for the time being. So what needs to happen here? You would take the second row, that's this one here, you would take the second row and you divide the whole thing by 7 because you have a 7 in this entry and you want a 1 in there. So this would become, 1 on 7, and this would be a 1 and a minus 1 on 7, and so on and so forth. So you divide that thing by 7, and then what would you do? You'd take 93 halves times row 2, and you'd zero out this thing, and then you would subtract 1/2 times row 2 to zero out this thing. And once you do that, your matrix now looks like this. And now, actually, we're going through all the steps here one by one, so you can see that. So take row 2, divide the whole thing by 7, and you get this. And now I also am going to relabel that with an x3, just so I can remind myself, hey, by the way, this row is no longer the row corresponding to basic variable x5. It's now x3 instead. So it's important to remember that you do that. Okay, so all I did is I divided row 2 by 7, and I got that. Okay, and then next I take 93 halves times this row, and I added it up there. So when I multiplied row 2 by 93 halves and brought it up to this row, I get this row there. And in particular, now I've got this 0 there as I want it to be. Next, I would say that you want a 0 over here, which means you should subtract 1/2 times row 2 from row 1, and now I've got a 0 like that. And now look, I've got my new table. All I had to do was, in this case, change 3 rows, and in doing so, I now have a tableau for my new basic set for x1, x3, x6, which is just what I wanted. And now you know the simplex method. Okay, that is really all there is to it. So in the simplex method in standard form, you're given a linear program, minimize some linear objective function with equality constraints and non-negativity, and I would have to, for now, give you an initial corner x bar, and I would have to give you the basic variables to start with, right? I would give you a linear program, and I would say here is, the basic set x2, x4, x6, or whatever it is, and that's the corner that you start at. Okay, so what's the first step that you do? Write the input C, write C in the top row of the tableau, write the coefficients A in the tableau, and write B in the tableau. And the upper right corner gets a 0. You'll see what that means in just a minute. You use Gaussian elimination to reduce the expression in terms of those basic variables. And then once you do that, you just repeat this same process that we've been doing. You ask, are there any negative objective coefficients? And if no, then you're done. And the upper right corner is -1 times the objective value, and the right column is the values of those basic variables. We'll solve an example, and you'll see what all this means. And then if the answer is yes, there are negative variables, then you perform this minimum ratio test. And we'll go through those steps here. I don't think I need to dictate all these rules to you. I think you'll learn it much better if I just work through the examples. And so let's do that now. So here is a new linear program that we'll start with. It's a pretty simple one. It has 4 variables in it, and we're told to start at the corner 1, 3. So step number 1 is to build this tableau. And you'll notice here I'm using these Roman numerals to refer to these rows. You don't need to write those when you're working through the tableau. They're just useful in this lecture so I can indicate, which row is being added to what in an unambiguous way. So the very first step, I call this step 0 because it's like initializing the whole problem. All you do is you say, okay, I'd write a -1, a -2, and a 2 in this first row like that. And you put a 0 in the upper right-hand corner. That's from this step back here. When I said the upper right corner gets a 0. And then what else? Then I just copy the coefficients of the constraints like that. I just copy these things over here. I put them in there. And then the 8 and the 9 goes here like that. Okay? So I do that. And what do I need to do first? The very first thing I need to do is I need to use Gaussian elimination to reduce this system in terms of x1 and x3. This is the longest, most arduous part of the simplex method because you have to do all of your row elimination for all of your basic variables. We only have 2 here, so it's not so miserable, but it is a thing that you have to do. So we have to reduce the row so that what happens? We want x1 to only appear in this second row, so we're going to have a 1 there, and we want zeros here and here. And then x3, we want to only appear in this third row, so we want a 1 there, which we happen to already have, although that's almost certainly going to go away, as you'll see in a minute. And then we want zeros over here. So that's the row elimination that needs to happen. Okay, so let's go through that process. The very first step that you have to do is the following. We want a 1 over here. And so we'll divide that second row by 2. So we'll divide the whole thing by 2, and we'll get a 1 and a 1 and a 1 and a 4 there, like that, because I just divided that whole row by 2. And then I would say, okay, I have a -1 up here, and I have a 1 down there now. So I'll add that 1 to this thing and 0 that one out. And if I add all of these, if I add row 2 and add it up to row 1, I would get these entries here. And then finally, what needs to happen? I have a 3 down here that I want to 0 out. So I would take row 2, multiply it by -3, and add it to this third row there. Okay, and once you do that, you get these entries over here. Okay, so now I've done that. Good. So x1 is fine. x1 appears correctly. It's only in that Roman numeral 2. And now we do the same thing for we'll do the same thing for x3 at this point. Now we'll look at x3 and we'll say we want the back one there. We now want to have x3. So if I'll erase all this stuff here, I'd say I want this thing here to be I want this to be a 1, and I want zeros up here and up here. So we'll do that. And that looks like this. Boom. There we go. And so it needs to happen. So this thing has a -2 here, and I want that to be a 1 because the coefficient of x3 has to be 1. So you divide that thing by -2. You divide this whole row by -2, I should say, and you get these entries here. In particular, there's that 1 that you wanted. And then once you've done that, you want to 0 up here where there's presently a 3. And so you would multiply this third row here by -3 and add it up there and 0 this thing out, and that would make all these changes to this row. And then you would just subtract that third row from the second row and get what you see here. Okay, so now I'm good, and I've written the simplex tableau for the first iteration of my simplex method, of my whole simplex method process. And so now what do I do at this stage? I look at my tableau and I say I am not finished because I've got a negative objective coefficient here, x2, and that tells me, okay, x2 is going to enter, and now I have to ask, is x1 going to leave or is x3 going to leave? And how do I determine that? It's with the minimum ratio test. And how do I determine which of these variables leave? I take 5/2 and I divide that by 1/2. And I take 3/2 and I divide that by 1/2. And I ask which of those is smaller. Of course, it's 3/2 on 1/2, which is smaller, which now tells me that x3 is going to leave. Okay, so now I know that x2 is going to leave, x2 is going to enter, x3 is going to leave. And what does that mean my row manipulations have to look like? It means that x2 is going to enter, which means I want a 1 down here. because so x2 is entering, x3 is leaving, which means I want a 1 right here, and then I want zeros here and zeros here, or a 0 in each of those two entries. Okay, so you do your Gaussian elimination. You add 5 times the third row to that first row to zero out that 5 halves. You subtract the third row from the second row to get rid of that 1 half, and then you multiply that third row by 2 to turn this 1 half into a 1. Alrighty, so you do that, and now you've got a tableau that looks like this. And this tableau now is in terms of x1 and x2. This is not optimal because you've got a -1 here. Right, so it's not optimal, and so we've decided x4 is going to enter. And so what's going to leave? Now, you're going to do a minimum ratio test, and this is where you have to remember all those little details, which is that we've decided that x4 is going to enter, but remember that you only divide entries on the right by entries in the incoming column if the denominator is strictly positive. Okay, that means strictly greater than 0. And in this case, there's only this variable here that has that happen, because you've got a -1 here in the third row. And so you don't divide 3 by -1. That is not an operation that you do. You would look at this and you would say, well, there's only one positive value here that can act as a denominator, which means for sure x1 is going to leave. So at this point, I've now decided that x4 is going to enter and x1 is going to leave. So x4 is going to enter, x1 is going to leave, and you do your Gaussian elimination. And this one you'd be very happy about, because you got a 1 there and you want a 0 here and a 0 there. This is the kind of Gaussian elimination that makes you really excited, because all you have to do is add that second row to the first row and the third. So you have the wind at your back, so to speak. So you do that. And now you look at your solution and you say, oh, I'm done. There's no negative coefficients. All right, and now this is the best part about simplex tableaus, which is that all of the solution is completely readable from this tableau. This tells me that x4 is equal to 1. It tells me that x2 is equal to 4. Of course, the other variables, x1 and x3, are equal to 0. And so I've got my solution. And the objective value is actually this number here times -1. And that is always true. The objective value times -1 is always the value in the upper right. And so the objective function value is -8. So reading the solution off of a tableau is very, very simple. And so recovering it is straightforward. Let's revisit degeneracy here, now in the context of the minimum ratio test. So what should you do? This is a question that comes up a lot. What do you do if you have a 0 in the right-hand side of the tableau? Okay, what do you do if you've got a 0 here when you're running through that minimum ratio test? The answer is nothing special. If there's a 0 there, it is simply carried through with the numbers as if you would carry it through with anything else. Okay, so in this example here, we've got x2 is our entering basic variable. And so when we perform that minimum ratio test, we'd look at 6 divided by 3, and we would look at 0 divided by 2. And of course, 0 on 2 is the smaller of those because it's 0. And so you'd say, well, then therefore, x4 is going to leave because it has the smallest minimum ratio test, which happens to be 0. But we don't care. It doesn't matter. We just work through the steps as we would otherwise. Do your Gaussian row elimination as you always would, and lo and behold, in fact, you happen to have an optimal solution here because there are no negative objective coefficients. There's no reason for that ordinarily to be the case. That's a degeneracy of the first type. Okay, so 0 values here in the right-hand side are never a problem. I will also say another question that comes up is, what do you do if you have negative values in that right-hand side? My answer is, if you have a negative value that shows up here in your right-hand side, or actually in the upper right, that's fine. But if you have values here in that minimum ratio test that are negative, it means you have made a mistake. It means you have made a mistake because remember that these entries here are the actual values of the basic variables. right? Remember when I pulled that solution off of the simplex tableau at the end, and I plucked those values off and said, okay, x2 is equal to this value, x4 is equal to that value. That is always the case at any one of these intermediate iterations. Since a standard form problem always has to have non-negative entries, it means you're never going to see negative entries here on the right. So if you see that in an intermediate simplex tableau, you should go back and see where you introduced this, because it means you've made a mistake. Now, the other question is, what do you do if you have a 0 on 0? Okay, and again, the answer is you don't do anything special. What if you've got a 0 here, and I've got a -2 there, and then let's say there's a 0 over here? Okay, the question is, do I have to do anything special? No, you ignore it. This is a 0 in the denominator. You therefore do not consider it when you perform the minimum ratio test. That answer always holds true. So the basic rule of thumb is just a value of 0 in the right-hand side, completely fine. Just treat it like you would treat any other number. And then always remember that you're only ever dividing by strictly positive entries. As long as you remember those two steps, the simplex method is perfectly well defined, and you're never going to run into any sort of scary, unforeseen circumstances.